This video is for Math 116, and this is the first section or first part of section 1.9, which is all about optimization. And the general idea here is comes from the calculus course. Calculus has methods for calculus is a lot of differential calculus is about the slope of a curve, because the slope on a curve is going to be changing depending on where on the curve you are. So because of that, at a maximum value on the curve, or on a minimum value on the curve, the slope of the curve is going to be 0. Okay? So that's how this is approached in calculus. First, you have to have a formula or an equation for the curve. That's the part that we're going to talk about. We're going to use a calculator. We're going to use the graphing calculator to find these points. If you go on to calculus, then you will have talked about setting up the equation. In calculus, you will do the process where you actually find where the slope is 0. Okay? But we'll save that for calculus. In this class, we'll use the graphing calculator to find that point. Okay, so first off, in section 1.9, I've split this into 4 different sections, although the third and fourth section are pretty short, so I'll probably just do one video for them. But this first section is what I call analytic optimization. So this has to do with just a graph. It's not really a physical situation, but it so well illustrates these ideas of optimization that I really like these problems. Okay, so first of all, we want to talk about the distance formula, where the distance between 2 points on a graph is the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Now, I usually don't like to just put up formulas and tell you to use them. I like to talk about what they mean and where they come from. So, here's one point, x1, y1. Here's the second point, x2, y2. Okay? The distance between them can be thought of as the hypotenuse of a right triangle. Here's D right here. Okay? This side of the right triangle is y1 minus y2, because the y1 is bigger, right? This one down here, this side of the triangle, is x2 minus x1. Okay? So, if we use the Pythagorean theorem, d squared is going to be x2 minus x1 squared plus y1 minus y2 squared. Now, it doesn't matter whether you flip these around, okay? So I'm just saying that because this one is y1 minus y2, this one's y2 minus y1. In the end, it really doesn't matter which one you do. Why doesn't it matter? Well, let's take a look at it with some numbers. Let's say we did 5 minus 3 squared or 3 minus 5 squared. This is 2 squared, which is 4. This is negative 2 squared, which is 4. That's why it doesn't matter, okay? These will always have the same absolute value, although they may differ in sign. When you square them, you'll get the same answer, okay? So, it doesn't matter what order you subtract these in, but it is important to get the y's together and the x's together in those parentheses. So that's where our distance formula comes from. It comes out of the Pythagorean theorem, and we can use it to find the distance between points on a graph. Okay, let's see here. All right, so on the bottom of page 52, it says, express the distance of a point xy in the first quadrant on the graph of the parabola y equals x squared minus 4. Well, here's the thing. If you remember from our discussion of transformations, y equals x squared minus 4 is going to look something like this. It's the standard y equals x squared parabola pulled down 4 places. So our vertex is now down here at the point 0, minus 4. So there's a little sketch of that. These roots, I don't ask you about this. but these are positive 2 and negative 2, right? If you factor this, it's difference of squares, x plus 2 times x minus 2, and so y will be 0 at 2 and negative 2. All right, so what this is saying is, express the distance of a point xy in the first quadrant on the graph of the parabola from the point 5, 2. All right, well 5, 2 is going to be over here somewhere, okay? The point xy on the parabola, let's see here. So we just want to express the distance from that point xy and the point 5, 2 as a function of x. Well, we'll get there in a second. D equals x2 minus x1, x minus 5, all squared, plus y minus 2, all squared. Now, key thing about this question is the language where I say express the distance, and then at the very end it says as a function of x. See this y right here? That's not a function of x. Okay? So, we need to somehow express that y as a function of x. Well, there it is right there. Okay? So, let's replace our y with x squared minus 4. And so, here's the answer to that first part. Square root of x minus 5 all squared plus x squared minus 6 all squared. I encourage you to leave this alone. Don't bother to simplify it. We're not going to really need it for anything except to use the calculator with it, which we will get to in 1 second. Okay, where are we? Use the graph of the distance function. So we're going to have two graphs here. We've got our original graph, and now we're going to have a graph of this distance function to determine the point on the graph that is closest to this point right here. All right, so let's do that. So first, let me put this into the graphing calculator. I'll sketch it up on the board, and then I'll also show you on the camera what it looks like on the calculator. So, x minus 5 all squared plus x squared minus 6 all squared. Okay, let's see here. So I'm going to look at this in the standard window. Most of these problems are set up so that what we need to see is going to be in the standard window. So let me draw a graph of the distance function, and I'll do this in red to distinguish it from our original function. All right, what are we looking at here? Something like this. Okay. So let's see here. So there is what we entered with the square root x minus 5 all squared plus x squared minus 6. And then we look at the graph, and there it is right there. So it's that point at the bottom here. This point right here is the minimum value, right? Because if we're looking for the point that's closest to 5, 2, that's going to be where the distance is the least, all right? Okay, so we need to find this point. So how do we do that? On the calculator, let's see if I can do this properly. So there's the calculator. Let's get some focus on it. Okay, not bad. So here's the thing. What you have to do here is hit the second key and then trace. Second trace. Number 3, find the minimum. So I just typed a 3 there. It's going to ask you for a left bound, so that you just have to choose a point to the left of that minimum value. So there's a good point. I hit enter. Now it wants a right bound, so we have to arrow past there. There's a point to the right of the minimum value. We don't want to guess. We want to know the exact minimum. There it is, 2.545. Okay. All right, so let's see here. 2.546, because it was 5459. So x equals 2.546. And the y value on this, which remember is a distance, okay? So the d here, and these are approximate values, they're irrational. Although this one may be exact, it's hard to tell. But anyway, 2.5 is a good approximation for that distance. Okay, so here's the first part of the answer, is the distance as a function of x. Now, use the graph to determine the point of the graph that is closest. All right, well, we know the x value. It's 2.546. And we know the answer to part C. How far away is it? D is approximately 2.5. Okay? What we're missing here is what's the y value. Now, don't get fooled, because when you do this on the calculator, it's going to tell you x equals this, y equals this. But don't forget that y value is a distance. Okay? We want this y value. And so to find it, we need to take this x right here, square it, and subtract 4. So let's do that. 2.546 squared minus 4, 2.482. Okay, so 2.546, 2.482, it's just about right where I had put that xy point, okay? And there's our distance here, it's about 2.5, okay? All right, so that's the example problem that's on pages 52 and through 55. Let's see here, 2.482, right, okay. So there's the example problem. Now let's look at some of the problems that start on page 56 here. All right, and I'll give you this distance formula when it comes to quizzes and tests and stuff. You don't need to memorize that. Once you understand, I think that understanding that it comes from the Pythagorean theorem is really helpful to remember what it is, you know, because it's just a square root of this squared plus this squared. But in any event, like I said, I will typically give that to you when we're using it. All right, problem 2, we're working with the function f of x equals 6 minus x squared. Point on the curve closest to the point 1, 1. Okay, so again, drawing a sketch can be helpful. You can graph it on your graphing calculator if you want to. So these, the negative x squared is upside down. The positive 6 pulls it up 6 units. And so this graph looks something like that. These roots are going to be plus or minus square root 6. So they're going to be irrational values. Let's see here. So what is square root 6? About 2.45, so the 0.11 is going to be inside there somewhere, okay? So we're going to have some point over here, xy, that is closest to that 0.11, okay? All right, so first off, so in these problems, the quizzes and tests are typically worded more like that example problem that I just did. In the exercises here, I'm kind of skipping over that language that kind of lays out the 3 steps in solving this problem. But I'm still going to follow them. So D is going to be, let's see here, x minus 1 all squared plus y minus 1 all squared. And then, remember the trick here is that we have to write this as a function of x. So, we're going to go in and replace y with 6 minus x squared. And you can leave it like that if you want to. I'm going to clean it up a little bit. This is going to be 5 minus x squared all squared, right? Because you got a 6 minus 1, so that will give us that 5 there. Okay, so now we have to graph this. All right, let me just show you this one as I'm typing it in. Okay, so we want the square root of parentheses x minus 1 all squared plus, there we go, plus 5 minus x squared, close parentheses, all squared. All right, so there's our function, and then we're going to go and graph it. And there it is. And then you can see on the right-hand side, you can see that minimum value again. And so here we go, second trace, choice number 3. And then we have to set a left bound, use the arrow to get over there. And it doesn't matter particularly exactly where it is, so long as it's to the left. So that's a good left bound. That's a good left bound. Now we need a right bound. That's a good right bound. That's a good right bound. It doesn't make a whole lot of difference. And there it is. Okay? So let's write down that information here. So the x value is 2.175. And the distance, remember when you get y on this, right, on this graph, like this, right, x equals 2.175. Now it'll say y, but really that's d. That is 1.205. Okay? 1.205. So, how do we get the y value for this point right here? Calculate 6 minus x squared. 6 minus 2.175 squared, 1.269. Okay? So, 2.175 or 1.269, there it is. Pretty much right where I had drawn it, but now we know what the coordinates for that point are. Okay? All right, let's see here. Well, let's skip down to number 6. We'll take a look at that one. Okay, so in problem 6, we've got a function here, 2x cubed minus 5x minus 1. And let's see, let's look at that graph. That one, I'm not going to be able to just draw a little sketch of. Let's take a look at it. 2x cubed minus 5x minus 1. What is that going to look like? It's a kind of a standard cubic doing this. Okay. Alrighty. Let's see here. And then what do we want? Closest to the point, -2, +8. So where is that going to be? -2, +8 is going to be up here somewhere. So we've got two possibilities, and we'll see that when we graph that distance formula. xy might be down there, but it might be over here. I'm not sure. Okay? We'll have to look and see what happens when we graph the distance function. But in any event, our distance function is going to be x minus -2 all squared, y minus 8 all squared. So let's clean that up. Like I said, you don't have to expand these, but it's helpful to do a little bit of simplification just to make it easier to work with. This one's going to be 2x cubed minus 5x minus 1 minus 8. So what we're going to end up graphing as the distance function is going to look something like this. Okay? All right, so let's go ahead and enter that. All right, square root x plus 2 squared plus 2x cubed minus 5x minus 9, and that's also squared. All right. Now let's take a look at what this graph is showing us. And there are those 2 points that I was talking about. It looks like the closest point is in the first quadrant and not in the second. Okay? If I open up my window a little bit, I'm just going to move that y maximum. I'm going to change that to be 15. And then we'll see a little bit more of that distance curve. So there it is. There's those 2 minimum values. It looks like the one on the right is a little bit lower, though. Okay? And if you're interested, how I opened up that y maximum is just in the window button right there. Okay? All right. So let me put a sketch of our distance function on the board. And I'll find both of those values too, and we can actually see which one is closer. Let's see. Okay, so this is doing something like that. Let's go in and find out where these are. Okay. So this one is x equals 2.136. And what's the distance there? 4.140. Okay. What about over there? Okay, negative 0.929. And what's the distance there? 6.05. So yeah, it's pretty clearly, this one is pretty clearly the closest one. And so that is the first quadrant point up here, where x is 2.136. We know our distance is going to be about 4.140. And now we need to calculate this based on x equals 2.136. So let me just show you a little trick for how to do that. So first, to come back to the calculation screen, you hit second mode, which will quit you out of the graphing. Come on, let's get some focus here. There, no. See, it's still focused on the board, so let's try one more time here. Okay, there we go. So what we want to do here is enter that x value, 2.136, and then see this little arrow over here that says STO? Hit that, and then the X button. There's what it looks like on the screen, and then hit enter. Okay, now that's stored as x. So I can just go 2x cubed minus 5x minus 1. There it is on the screen. You can see 2.136 has been stored as x. Then I make that calculation. There it is, 7.811. And that's our y value. And here it is here, 7.811. There's the point that's closest, there's how close it is, and there's our distance function, right? So these are the three pieces that I'm going to be asking you for when this comes up on the midterm, okay? All right, so that was problem 6. So let's wrap this up with problem 8. This is a geometric optimization. I see these a lot in calculus textbooks. It depends on who your instructor is and how much they like these geometric problems. Some of them are pretty interesting, and some of them are really useful for particular problems in industry. There's a lot of geometry out in the world out there. I remember a former student of mine asking me once about how to build. They were building this hemisphere dome on a ship to put over a tank. I think it was a fuel tank, and it came in pieces. It came in pieces, and the question was, how can you weld those pieces together? Because they didn't come pre-cut. They come kind of like this, where the edges are rough, and then you've got to cut them out yourself and fit them together. And that can be a little bit tricky. But it was considerably cheaper than ordering it and having it shipped pre-made. So those kinds of geometric questions really do come up in everyday life, or at least in industry. And that's the reason why these problems pop up in textbooks like that. Okay, let's look at problem 8. So problem 8, we've got a semicircle like this. Well, let me move my y-axis so that we're centered. Yeah, that's better. Okay. So the equation for this is square root 25 minus x squared. So it's half a circle, right? The whole circle would be x squared plus y squared equals 25. We'll talk about that in, I think it's chapter 2. Okay, radius of 5. So we know that that's 0, 5, that's 5, 0, and negative 5, 0. So the problem says a rectangle is inscribed in a semicircle of radius 5. 2 corners are on the x-axis and 2 corners are on the semicircle. So that's going to look something like this. Express the area of the rectangle as a function of x. All right, we know the area of a rectangle is the length times the width. So we need to express those as functions of x. So come down here, there's the origin 0, 0. This distance right here is x. This is the point xy. So the length of this rectangle is 2x. Okay? Now we need to express the width right here. Okay? That's the y coordinate. That's the square root of 25 minus x squared, right? So here's your length, here's your width. This is the area function right here. 2x times square root 25 minus x squared. All right, so that's what we want to graph. Let's see, 2x outside the square root, then inside the square root, 25 minus x squared. Okay, and let's look at the graph and see what it does. This is our area graph. And it goes a little bit off the screen here. I think I'll open up my y coordinates and see if we can get a better look at it. It's kind of an interesting shape. Let's see here. So it's kind of doing something like this, okay? And then it stops because for x values greater than 5, there's no rectangle. Okay, and that's why we're not getting any area calculations there. And if you look at the formula, what that's going to do is that's going to put a negative underneath the square root and generate a complex valued answer. Okay, there's nothing wrong with complex answers other than in a lot of physical situations it's kind of hard to see how they relate to the situation, but they are kind of interesting. Okay. So let's see here. What do we want? Express the area. For what value of x is the area largest? That's this point right here. That's still not on my screen. So I got to go into the window, make my y maximum even larger. Okay, so there we go. So now I've got this set up. Okay, you can see I've got that y maximum there on the right over here. Okay, my screen is set up so that y maximum is at 25, so that we get a good look at that. So now we go second trace, number 3 is minimum. We want number 4 this time, maximum. All right, but we're still going to set a left bound right there, let's say, and then arrow past it. There's a right bound, and there's our maximum point. X equals 3.536, y equals 25. Okay, so let's see, did I move the screen a little bit? Oh, okay. All right. So what do we got here? So that point is where x is 3.536, and the area is, well, the area is exactly 25. Okay? So, let's see here. So the coordinate, x, well, let me switch back to the purple one. X equals 3.536. Our maximum area is 25. And then, we need the y coordinate. So again, let's see here. I'm going to store this value as x. And that's an important part, because if you don't change what the value of x is, it's just going to hold on to what you stored in there last time. 3.536. All right. And then we hit that STO key right there, and then we want to store that as x. And there's what it looks like. Okay, and then we type in square root 25 minus x squared, and that'll tell us what y is. Oh, the y is the same. Okay. All right, so y equals 3.5, it's actually 535. And let's see, let me double check that I got that other point correct. I'm not sure if those are actually the same number. No, they're just very, very close to each other, which is kind of interesting. At first I thought they were going to be the same, x and y were actually going to be exactly the same, but as it turns out, for some reason they are very close to each other. However, they're off in the thousandths place. Okay. Well, so that's it for this first part of section 1.9. Like I said, I'll probably do 2 more videos on this next week. One for part B, which is about more geometric optimization. And then I'll do one video on those last 2 types of optimization. And then I'll do a video for a sample midterm, okay? Because we're going to have the midterm coming up week after next. As always, if you have any questions, please let me know. Thanks.